Okay, so for the final hour, I thought I'd talk about once you've read in your data, a few data auditing procedures, how to look at your data and how to make sure that everything's in a proper format before you start analysis. So if you were still working with the ant2_analysis_r file, and we're looking at the section that starts with looking at data. So previously we read in the all subs. We read in all the data. Does anybody not have that working yet? No, it all works. So if we click our workspace, we should have an object, data file object called all subs. It should have 5,760 observations. Yeah, okay. All right, so I want to create a copy of all subs because I'm going to mangle it in a second, and I don't want to have to run this whole function all over again. So the copy I'm going to call A. Again, just arbitrarily because it's nice and easy to type. So I'm going to say A equals all subs, and we'll just run head of A to show that these are the first 6 columns in A. So I've already showed you head of A. That's one way of looking at your data. You can also look at your data by clicking the workspace and clicking the object that you're interested in, and it will open up this little browser. You can see that A has lots of 7 columns and lots of rows. A way to summarize the information in A is the easy_précis function. And that's like the variable view in SPSS, where we can see what sort of data type each of the columns are, whether there's any missing data in any of the columns, if there are, or the number of unique values in each of the columns, the minimum and maximum, which is somewhat meaningful in the context of, or is meaningful in the context of numeric variables, can be a little helpful in the context of factor variables insofar as it tells you what the first level of a factor is and what the last level of a factor is. Let's look at some other ways of looking at the data. So if I wanted to look at the first 10 rows and the first 3 columns, I can use this syntax here in example 3. So I have A and then square brackets. Inside the square brackets, I have something, comma, and then something else. The thing before the comma is a way to specify what rows you want. The thing after the comma is a way to specify what columns you want. So here I'm saying I want rows 1 through 10. Remember, that's what the colon means. And I want columns 1 through 3. And when I run that, it's just going to print that section of the data object A to screen. So first 3 columns, which are subnum, block, and child, and the first 10 rows. If I wanted to look at the first 10 rows, but all of the columns, and I didn't want to try to count how many columns there were, say I didn't know how many columns there were, I can just omit the column selector. That is the thing to the right of the comma. So we have A square bracket, something to the left of the comma, but nothing to the right of the comma. And that will show me the first 10 rows of A and all of the columns. So you can see that head of A is exactly the same as just doing A 1 through 6, comma. If you wanted not all of the columns, but a non-sequential subset of the columns. So let's say I want to see the first 10 rows, but I only want to see columns 1, 4, and 6. You can do that, but you have to specify 1, 4, and 6 as a vector, which is achieved by putting them inside the C function. So on the left, this expands as 1 through 10, and this will create a vector 1, 4, and 6. It runs, and we get columns 1, 4, and 6. Now, in this next example, if I want to just get the names of the columns of A, I can use the names function. The names function can be run, and you just get a vector of strings representing the names of each of the columns. I can select columns according to, I can create a list of columns selecting according to the name of the column. That's what's being done in the second line of example 6, except that I'd like you to replace the letters ID with subnum. And the same for the third line of example 6. You've got the word ID there, and instead you want to type subnum. Again, this code was referring to a slightly different set of data that had slightly different names for things. So by turning it from ID to subnum, we're referring to the names of the, we're using names that that are actually in the data frame. So the first row, the first line here within example 6 simply asks, what are the names of the columns in A? The second line uses the in operator. What's to the left of the in operator is familiar. It's a function that will return the names of the columns in A. What's to the right of the names operator is just a vector of strings put together by the C function. So what does the in operator do? It asks, it will test each thing on the left-hand side and check to see if it is in the thing on the right-hand side, and anywhere in the thing on the right-hand side. So if I run this, what it's going to do for each column name, it's going to ask, is it in this list of names on the right-hand side? So subnum was the first element of names A. It definitely is in this list here, because it's right there, subnum. Block is the second item in the vector returned by names A. It's not in the thing on the right-hand side, so that returns as false. Same with trial. Q and flank are in this list, as is RT, but error is not. So for each of the names, for each of the columns, we get a logical vector indicating whether that column's name was in this list that I provided here. Why am I doing this? Well, because sometimes if you want to have just certain columns from your data frame, it's useful to refer to them by name instead of by the number. So the way to do that is to pass as the column selector a logical test of whether each name is in the list of names that you want. So if I just want to see the column subnum, Q, flank, and RT, I will pass names A in, and then the list of names that I want. And here I also keep that row selector 1 through 10, just so the output is manageable. So if I run that, it's just going to return rows 1 through 10 in the columns subnum, Q, flank, RT, just as I wanted. Example 7, again, refers to ID, so we're going to change that to subnum. So $A subnum equals factor $A subnum. We're doing this if we recall, I guess, above, if we just run easy précis A right now, before running that, subnum is numeric. Really doesn't make sense to leave that data as being treated as numbers. It's much safer to have it treated as a factor. So that's what this is doing. It's replacing the contents of the subnum column within A with the result of the thing on the right, which is just taking the contents of the subnum column within A and turning it into a factor using a factor function. So if we run that, as well as the easy précis, you'll see that we indeed successfully turned subnum into a factor. So that's pretty common when you're reading in data that you previously labeled all your subjects numbers. You have to explicitly go and correct things to tell R that it's actually not a real number, it's a factor. Another thing that happens pretty commonly, that at least commonly enough that I've had people complain about it or ask me about how to do this, which is sometimes the reaction, if you have a number, something that's truly a number, it can get turned into a factor. Just maybe you have a space in your RT column somewhere, or a weird string that wasn't properly defined as an NA value. So to simulate that being the case, what we should do is run this first line, which will replace the contents of RT with a factorized version of the RT column. And we'll call easy précis to make sure that what we did was indeed, yes, we turned RT into a factor. So the point of doing that was I wanted to show you how to undo it. How to take a number that's really, or a column that's really supposed to be a number, but was read in as a factor, turn it into a number again. The first guess of most people is to use the as.numeric function. As.numeric, if I say as.new, and I put the string 1, so it's a string because it's inside quotations, it will turn it into the number 1. So as.numeric has something to do with turning things that aren't numbers into numbers. However, if we try that, so we say ART, replace its contents with the result of calling as.numeric on that column, and run easy précis. The consequence is, well, RT is now numeric. Hooray! But wait a second. Its minimum is now 1. Its maximum is now 5616, which is suspiciously close to the number of levels in A. So what's actually happened here is that instead of going from the character string that describes the level of the factor for each RT, it's actually gone and retrieved the number corresponding to basically the numeric order of the RTs. So in something, again, let's take the example of the flank column. The flank column has 3 unique values. If you want to see what those 3 unique values are, you can look at table a $flank. You can see that there's congruent, incongruent, neutral. The number underneath lists how many trials, or how many rows in the data are associated with that label. So there's 3 levels of flank as a factor. If I were to take this and say table as.numeric flank, congruent is the first level. And what's happened is that as.numeric has grabbed the level value of the factor level instead of trying to turn the name into a numeric. Here with flank, congruent can't be turned into a numeric, even if it were just a string. But the idea here is that factors have labels, and that's what you're typically seeing here. Congruent is the label for but it also has levels. So congruent is the label for the first level of flank as a column, as a factored column. So in the context of RT, when I turned it into a factor, it went through, it gave every number a level and took the value of the number and assigned that as the label. And when we tried to turn it back into numbers, it ignored the label, which is the actual number that the RT that we want, and just grabbed the level number. So you're going to get the numbers 1 through however many unique levels you have. So what you have to do instead, we'll move on to example 9 because that fixes things. So example 9 will rerun the original creation of A. So this is why I created this separate thing A, because I knew I was going to mangle it. So we're going to create A again because it's just a copy of something else we read in, the all subs. We're going to turn RT into a factor, pretending that that's how it was read in erroneously. We can confirm that RT is a factor by running easy-pray-c. We indeed see that RT is being treated as a factor. And the idea here is to get a factor whose label is the thing that you want to turn into a numeric. You have to turn the factor into a character first. So RT is currently a factor. We're going to turn it into a character, in which case R will grab the label, and then we want to turn the label into a number. So that's what those two last. So the last thing is calling easy-pray-c to confirm that it's a number, it has a reasonable minimum, maximum, and we're back to where we started. Other ways of looking at your data. So the next example is going to use a new function we haven't seen yet. We'll also see our first picture, our first graphic from R. So it's the easy design function. It's if we take a look at the help for easy design, it's a function to plot the balance of data in an experimental design. This function provides easy visualization of the balance of data in a given data set given a specified experimental design. This function is useful for identifying missing data and other issues. So easy design has several parameters, or several arguments. So one argument's named data, pretty self-explanatory. It's the data frame that you want to visualize. We're creating a graphic. So the graphic will want a variable to map to the x-axis, another variable in your data frame to map to the y-axis, and if you want, you can split the plot into multiple facets, either by rows or by columns or both. And the cell border size is something that tweaks an aesthetic thing about the plot that I won't show you yet. So let's just run easy design. So we want to supply as the value to the first argument data, the data frame that we want to look at, so it's A. We also want X to be the Q column. Now, you can go ahead and so there's actually this weird period parenthesis going on here. That's Easy's way of saying that this column exists within this data frame. It's a little idiosyncratic to easy, but it gets nice when you have to list multiple columns to a single argument. It reduces the amount of typing you have to do. But recent versions of Easy have smartened up, and you don't actually need to put those here in this case. So I'm going to delete the period parenthesis on both sides. So we'll just have x equals q, and we're going to replace this whole thing, period parenthesis ID, with just subnum. So we've got easy design, data equals A, x equals Q, y equals subnum. So what this is doing is it's looking at data. It's going to say for each combination of Q and subnum, Q being a column in A, subnum being another column in A, how many rows are in the data. So I'll run this. It will run in the console, but then immediately pull up a plot graphic from the plots tab. So what you can see here, there's 4 levels of Q, there's 20 levels of subnum, and everybody has the same number of observations. If there were different numbers of observations per cell, you'd see that by a difference in color across these. Let's do the same thing, except, so in example 11, we're going to replace dot parenthesis q with just q, replace y with subnum, and delete the period parenthesis around flank. So here, we're again looking at, for each level of q, for each subject, and now for each level of the flank column, what is the balance of the design? All right. So this is what I meant by the visualization can split into different facets, so you can visualize combinations of, larger combinations of variables. So that's the balance of data overall. This means that everybody seemed to get the same number of trials per combination of the 2 variables that are in this data frame, flank and q, that are important experimentally manipulated variables. But maybe we're interested in a subset of the data. Specifically, in the context of reaction time research, we're typically interested in looking at only reaction times for trials on which participants made accurate responses. Because we don't really know what happens on trials where they made an error. So I'm going to subset. I'm going to look at a subset of A. So we're doing a subset, so we're going to use the square brackets, and we're going to have something, comma, something else. Well, I want all the columns, so I'm not going to put a columns selector. And I want to subset the rows. I only want those rows for which the value in the error column is equal to 0. The way to say that is to say $A$ER, which is the I might change that. I think it'll work regardless, but just to be clear, I'm going to type in the full name for the column. Sometimes R does partial name matching, so it might work if you just say ER, but I'm going to type the full name for error. So what it's going to do is it's going to grab all the values in the error column, and for each value, it's going to test it to see whether it's 0. If it is 0, which I happen to know means that the participant did not make an error, it's going to use that row. If it's 1, which is the only other option for values in this column, it will omit that row. So what we're doing here is we're just selecting those trials on which participants made a correct response. But we'll still use the same stuff from above, so I can actually just copy x, y, call from above, so x equals q, y equals subnum, call equals flank, and paste it over here. So now we've got data equals A subsetted, but we still have x, y, and call as above. If I run that, it's looking at a subset of data, and something's gone awry. Suddenly we have this NA thing going on with the columns. So let's actually just take a look at the data using easy précis. We can actually see that there's missing data, specifically for the ER column. I'm sorry, for the error column. So I tried to use the error column to subset using a logical test, but when the logical test encounters missing data, so there's an NA in the column, it's going to return an NA. And that's going to throw off the, its ability to use that as a way to subset the data. So what I'm going to do is just toss all those trials on which there was an NA in the error column, because that probably means that just nothing happened on that. Something went awry with the computer on that trial to have an NA in that column. If I run the same thing as above again, so I'll just copy that whole thing. Example 12 is being copied and pasting over top of the easy design in example 13. And I'll run it. Now the visualization will come up, and oh, okay, it looks a lot nicer. We no longer have that weird NA thing there. But what it's showing is that there actually is variability amongst the participants with regards to the number of trials that they have across the conditions. Things that immediately jump out is this blank space. So that means that participants never had any accurate trials in that condition, which is troublesome. Here's another blank space. They never had any accurate trials in this condition. What's also troubling is that there's a large range of number of rows. So for example, the darker red indicate 1, and the lighter, or the blue indicates, well, you can see the red and blue pretty decent. Okay. Yeah, indicate larger numbers. So clearly some people have very little data. For example, there's a person here. Let's see if we can zoom in a little bit. Yeah, number 12 has pretty dark red all the way across. Number 7 is kind of dark there. Might be something to look at. And number 14 is the one that just doesn't have any data across any of the Q conditions, specifically within the flanker and congruent condition. But they have a decent amount of data in the other conditions. Okay. So this next section is intending to show you how to manipulate data. We've already done a little bit of data manipulation, turning things into factors, or turning things from factors back into numbers, subsetting the data as we've done here by just tossing those trials where something wonky went on. This is going to be a little bit, so if we want to just get rid of an entire subject, so for example, this subject 14 made no accurate responses within a condition. So, yeah. So number 14 made no accurate RTs in this experiment. We don't have any observations for them in a condition of the experiment. So traditional tools such as ANOVA can't be, this person cannot be in the data set for those traditional tools to work. ANOVA can't deal with missing data. So what we can do is just toss that person. So the way one would do that is we'd be creating an object called A, into which we put a subset of the original object A. You know it's a subset because we're using square brackets. And we're going to grab all the columns, as evident by the fact that we're not using a column selector. But we are going to have just a subset of the rows. And specifically, what we're going to do is we're going to go through all the rows, all the values in the ID column. Oh, if you remember, we're going to change all instances of ID to subnum. All right, so we're going to go through the subnum column. And we're going to evaluate each value in that column. And we're going to ask, is that value equal to, and in quotation marks, 14? Why in quotation marks? Because we've factorized the column. So we're asking about the labels of the column. Is the label equal to or not equal to 14? If I put the equals equals there, it would grab all those rows for just subject 14. But I want to actually exclude 14. So I want to grab all those rows, those columns where this expression, where this value in that column is not 14. So that's what we're achieving here. So if we run this again, we change this again to subnum, and then get rid of all the parentheses. I don't need to get rid of the parentheses, I'm just, I guess, trying to be neat. So I need to get rid of subject 14, I'll run that, and then I'll just replot this graphic. All right, so if I maybe expand this graphic, 14 is gone. It goes 10, 11, 12, 13, and then 15. So 14 is gone, that big space is gone. 12 still seems wonky. Something's gone wrong with 12. Maybe I go into their data set and I go, oh, they switched the responses. They're supposed to press one key and they press the other and vice versa. So the error column is incorrectly coded for that person. 1 means they actually pressed the right key, and 0 means they didn't press the right key. So I can actually specifically change just those elements in the error column corresponding to that person's data. So I'm going to, why I missed it. So if I wanted to do that, probably best to expand that to the full name error instead of just ER. So anywhere you see just ER, just think as ERROR. And again, we don't have a column called ID, but we do have a column called subnum. And over here, don't have a column called ID, subnum. So what we're doing here is we're saying we're going to assign new values to the error column within A, but only a subset of the rows within the error column. That subset of rows whose corresponding value in the subnum column is equal to 12. 12 is the one we have, by other means, decided that they have just their responses switched, and we just need to switch their error thing around. So what we do is we say A error subnum, and if you've got a binary variable coded as 0 and 1, and you want to flip the mapping, you just say 1 minus the original mapping, and that flips it. So all 1s turn to 0, all 0s turn to 1. So we can run that. And then we update the visualization. Then replacing ID with subnum. And running this. Suddenly we see that that participant has a reasonable number of observations. Still have this sort of glaring row here where subject number 7 just has very few data observations. Maybe they did the same thing. Let's just try switching their data around. So we'll do the same thing with subject number 7 as we did with subject number 14. So we say subnum or, so take their original data and say 1 minus their original data, and fix this over here, subnum or. We run that, and then I'm just going to copy this here to make it so that we have no parentheses and ID is replaced with subnum. Run this all. So we've done the exact same thing with subnum number 7 as we did with subnum number 14, and we're simply re-visualizing the balance of data. And things got worse. Subnum 7 has even lower counts of data and indeed missing data now. So I don't think it's the case that they actually were flipping their responses. So we have to undo what we did a second ago, which is easily done. You just copy the code that we did to flip them and paste it down here under tangent to flip it back. Copy. So what we're doing next, we're visualizing the same things again. So x, y, and call, well, what I'll do is I'll delete the period parentheses, I'll change ID to subnum, and call is done. But we're adding yet another variable to visualize. We're going to have row as equal to block. I'm going to try to look at this data a little bit more to see why subnum 7 is missing so much data. So I haven't actually run the code to flip it, so I'm going to run the code to flip them back to the original mapping of errors. And I'm going to do another visualization of the data, this time breaking up things by block. This cell border size thing is just to make it so that the lines in between the little squares, you can make them bigger or smaller. By putting it to 0, it means that they're non-existent. So there's a reason it just ends up looking a little nicer for the following when you have really big visualizations as the thing that's kind of come up is going to be. So I will run this, and it will go. And I'll try to maximize this as much as possible because it's pretty dense. But what's happening here, you get a big solid block of blue for the block 1 in all of these things. And for block 2, you get a big solid block of blue. Block 3, you get a big solid block of blue. But then block 4, you suddenly get this band of empty data. Now, it's hard to see from the scrunched up labels on the axis there, but it's subject number 7 who is responsible for that band of empty data. If we go out to our files and we look at number 7, so I have to resize this to bring my file viewer back over. It turns out that that subject, we scroll down, there's block number 2, block number 3, block number 4 is all NA, block number 5 is all NA, block number 6 is all NA. So clearly they discontinued the experiment halfway through, and the data file just put NAs for the rest of their data. So we probably want to get rid of subject number 7. This next little section just focuses in on subject number 7. Again, we're using a selector on A, or a subset of A, using a row selector, but keeping all the columns. So we want to just look at those columns for which the value in A subnum, not AID, A subnum, is equal to 7. And we want to look at Q's, map the Q's to the x-axis, block to the y-axis, and have different facet columns mapped to the different levels of flank. And we can see that this participant only has 3 blocks worth of data. All the rest is missing data. In contrast, if we were to look at subnum number 8, run the same thing, they all have 6 blocks. So clearly, the subnum number 7 just discontinued the experiments halfway through. You might reasonably keep them in. Maybe they can contribute some data. ANOVA would treat them equally to all the other participants, which is maybe not what you want to do, since they have half the data. Your estimates of their means are going to be half as reliable. More complicated statistical tools, more nuanced statistical tools will appropriately take into account that they have half the data. I'll talk about those on probably Wednesday. So we're still trying to just talk about modifying data. So far I've been talking about subsetting the data and tossing out whole people because of their behavior, or modifying the data in a column. If I want to create a new column, that's what's happening in example 3. So I'm going to create a new variable in A. So I'm going to say $sex. And I happen to know that all the even numbered participants were male and all the odd numbered participants were female. I was diligent about my data collection and wanted counterbalancing across time of gender for some reason. So if I wanted to reflect that as a column in the data, well, I need to make some sort of numeric evaluation of the, well, I've got AID here. I need to change that to A subnum. But we know that we've already converted A subnum to a factor. So what we need to do is do that, convert it to a character, and then convert it to a number. We don't need to store that anywhere because we're not going to use that information anytime. So you can just do it in the inside this function, this if-else function. So what the if-else function does is it makes a logical evaluation, and then if it's true, it assigns this level or this value to the row, and if it's false, it assigns this value to the row. So because we're doing this logical evaluation, the subject number as a number, mod 2. So the question is it evenly divisible by 2? Yes or no? If not, then it's going to be equal to 0. Sorry, if it is evenly divisible, it's equal to 0. If it's, so this would turn out this whole expression for those subjects that are, whose subject number are evenly divisible by 2. This expression will be true. For those subjects whose subject number is not evenly divisible by 2, this will evaluate as false. Because we have as many rows, evaluations as there are rows in the subnum column, we'll have as many output values as there are rows in the data frame. So we'll have a new column. Each column will, that column will label each subject as to whether they're a male or a female. So run that, and I'm going to get rid of our plots and resize this a little bit. And if we say easy précis, we'll see that we now have a new variable sex. It's a character variable, so it's a string or a character. Has 2 levels, male and female. Oh, I guess subnum was numeric. We forgot to refactor it after we redefined A. So we should maybe do that now. A subnum equals factor A subnum. If we do that, we can run easy précis again. If you ever need to repeat just in the console something you typed above, you could just retype it, but you can also press the up key. So I can redo that, or I can redo that. So it's that one that I want to do, and so I hit return. So now subnum is a factor, as it should be, because it's not really a number. And sex is still a character. Probably want to turn sex into a factor, because it is something that will have discrete, will have, I guess, identifiable levels. Maybe we want to use it as an experimental, or not an observed variable in our statistics. So we'll say a sex equals factor, a sex, and then we can look at just the balance of design, putting sex on the x-axis and subnum on the y-axis. By the way, I tend to put subnum on the y-axis because there tend to be a lot of levels of subnum and longish. I guess there's no good reason now that I think about it. So here's what it looks like. There's subject number 7, who didn't have nearly as much data as everybody else. They indeed have about as much data as everybody else. But otherwise, you can see there's this alternation. We hit here, that's where we can see that subject number 14 was taken out. So the alternation skips a little bit, but then goes back. Just to demonstrate that you could look at it either way, I'm going to say put sex on the y-axis, subnum on the x-axis, that way, and that's another way of looking at it. So when you do your calls to easy design, which aesthetic attribute you specify for what variables is largely a matter of just aesthetic preference. Well, I think I'm going to, the next section is actually a little long, so it would go over time. So I think I'm going to cut us off there, make up for the fact that I went over time on the last section. Does anybody have any questions on what we covered in this last section? I guess manipulating things, using selectors and subsets.